Let's talk about the variability in our predictions. The way we make a prediction is as follows. We start with some data and we're trying to predict the response variable, y, by the values of the predictor variable, x. And what we do is we first fit a regression line to our data, and then we look at the y-coordinate of the regression line at our given predictor value. And that y-coordinate of the regression line, the height of the regression line, is our prediction, point prediction, for the response variable. And the idea is that the regression line is really close to the true line, so this y-coordinate on the regression line should be close to the y-coordinate on the true line. But it's always better to give an interval rather than a single point predictor, right? When we give an interval, we indicate not only what we think the prediction might be, but we're also indicating the something about the precision of the prediction. And so here's a way to construct what we call a confidence interval for prediction. And to do that, we'll do it in the following way. We're going to bootstrap the scatter plot. That means we use the table that we start with, and then we use the dot sample command, and we can just leave the parentheses after the dot sample command empty. And the defaults there will sample rows from our original table with replacement until we fill up a new table that's as big as the original table, that has as many rows as the original table. And so we get this new table, and then we fit a regression line to this data in the new table. That might give us a slightly different regression line. And if we evaluate the y-coordinate of that regression line at the x-coordinate that we're given, that will give us a new prediction. And then we can store this new prediction in an array, and we can repeat this process many, many times until we have an array with many values, maybe 200 or 1,000 or something like that. And if you'd like, you can draw the empirical histogram of all these predictions, and you can kind of see the predictions graphically. And then you can use the percentile commands to get the middle 95% of these predictions by taking the 2.5 percentile of the array and the 97.5 percentile of the array of predicted values, or sometimes called fitted values. And those 2 percentiles will be the left and right endpoints of a 95% confidence interval for the height of the true line at x. But if you had a different x, then of course you'd get a different y value. After all, as you slide x along the x-axis, your y-coordinates should slide along the regression lines, and so we should get different predicted values for y. And that makes sense, right? Y is correlated with x. As you change x, you should be changing y. And what's not so obvious, but is true, is that the width of the prediction interval also depends on x. And when I say prediction interval here, I mean the confidence interval for our predictions. And so typically the intervals, confidence intervals for our estimates near the mean of x, near the kind of center of the x values, is narrower than for x values that are further away from the mean. This is a helpful thing to know. Okay, let's go to the demo and see this in action. Let's use our model to predict a baby's birth weight if it had 280 gestational days. And we can use the function that we defined earlier, fitted value. We feed it the baby table, the predictor variable, gestational days, the response variable that we're trying to predict, birth weight, and the predictor value, in this case 280 days. And it tells us that just a little bit under 120 ounces is our predicted value. That's the y-coordinate of the regression line going through the baby data when you're looking at x value equal to 280. But this is just a number. It's a point value number, and that number would jump around if we had a different set of sample observations. So what we could do is we could understand how that number would jump around by doing some simulation and bootstrapping, right? So we'll do 1,000 repetitions of the following process. We'll start with our predicted value of 280, and that won't change for us here. We'll make an empty array of values, fits, and I'll store my predicted values here. And then I will loop 1,000 times through this indented code. And what I'll be doing in the first line here is to use the .sample command to bootstrap a new sample from the baby table. This is new data, and this data has been created by resampling. And then we'll use our fitted value command, again with the predicted value of 280, to predictor value, I should say, 280, in order to calculate our new fitted value, our new fit number, and that's our new prediction. And then we append that prediction into our array called fits, and then we make a histogram out of this. And here's the various predictions that we had. You can see 120 is a pretty common prediction, our point value that we got. But now you get a sense of the variability of these predictions too. Maybe something like between 119 and 121 seems like a pretty common range of numbers here. If we wanted to make that precise, we could take a 95% confidence interval and calculate the 2.5 percentile and the 97.5 percentile as our left and right, or low and high numbers for our confidence interval. And here you can see that 95% of the simulated values were between 118.92 and 120.87, and that is a good 95% confidence interval for our predictions of the birth weight for a baby at 280 gestational days. And you can see that that our predictions aren't going to vary very much, right? They go from 119 almost to 121. They're only differing by a couple of ounces, right? Okay, what if the gestational days was 330 instead of 280? Let's check to see what our model would predict. Okay, we can do the same thing. We can do a bootstrapping procedure with the predicted value being 330 instead of 280, and everything else here is essentially the same. And what we get is a point prediction of 143 ounces, about 20 ounces more than the baby born at 280 days. And that makes sense, right? We were always predicting that the baby's weight would go up as it spent more time in the womb. But here's the interesting thing. The confidence interval goes from 139 to 148. That's 9 points. 9 points is huge compared to 2 points up here, right? Here the confidence interval for our predictions is really, really wide. It's much wider than it was before. And if the thing that's explaining this is that the mean value for gestational days, the mean value for our predictor is 279. So 280 is really close to the mean value and should have a narrow confidence interval for our predictions. But as we get further and further away from the mean value, like 330, that's 50 units away from the mean value, then the lines spread out. The regression lines, small changes right near the mean end up propagating into bigger changes further away, and we get a wider spread of predictions. So our predictions further away from kind of the central value of our predictor are going to be more variable.